All right, everyone. Hello and welcome back to Regression Analysis, video number 10. This video is going to talk about sections 11.1 to 11.5 of chapter 11, which is variable selection procedures. So section 1.1 is just a little introduction. So far during this course, we assume that the variables have been chosen in advance. There are some cases where theoretical or other considerations can determine the variables. In that situation, variable selection does not apply. So variable selection becomes an important part of the regression equation when there is no clear-cut theory. So variable selection and functional specification are indeed linked with one another. And the main question here is what variables should be included and in what form should they be included in? So the examples of forms that the book gave were the transformed variables, the original variables, or a combination of both, transformed and original. All right, so section 11.2 went on to talk a little bit about formulation of the problem. So a linear model that represents y in terms of variables is represented by this model up here, which is y sub I equals beta sub 0 plus our summation of j equals 1 to q. That summation is going to include beta sub j times x sub ij plus r epsilon sub i's, where our beta sub j are our parameters and our epsilon sub i's are our random disturbances. So during the videos for this chapter, we will discuss how to determine which variables are to be retained in an equation. So we're going to go over a little bit today and in the rest of chapter 11, which is probably next week. So the effect of variable deletion can be examined under two conditions. The first is that the model connects the y to the x's and has all the betas as non-zeros. And the second would be our model has our beta sub 0, our beta sub 1, all the way up to our beta sub p as non-zero, but beta sub p plus 1 all the way up to beta sub p, which indicates our deleted variables, as 0. So we can instead fit this model here at the bottom when we have our deleted variables. So this would be our y sub I equals beta sub 0 plus our epsilon summation of j equals 1 to p of beta sub j x sub ij plus epsilon sub I. So these are pretty much the exact same thing. We're just going to deal with our deleted variables in this case and our original variables in this case. So 11.3 is going to discuss the consequences of variable deletion. So denote the estimates of the regression parameters when using the original model as our beta sub 0 star hat all the way up to our beta sub q star hat. And our model with our deleted variables is going to be indicated with our beta sub 0 hat all the way up to beta sub p hat. So the only difference between our model with the original variables and the model with the deleted variables is we're going to take away the star with the deleted variables, and we're going to change that q to a p. So our y sub I star hat is going to indicate our predicted variables from the full set, which includes our original variables, and our y sub I hat is going to indicate our predicted variables from the partial set, which is with the deleted variables. So we're going to see the same thing with the predicted variables like we did with the models, is we're just going to take away the star when we move into working with our models with the deleted variables. And our variance of b sub j star hat is always going to be greater than or equal to our variance of beta sub j hat, and that is for all j's 0 to p. So the deletion of variables can never increase the variance of the estimates. The better way to compare the variances is by the mean squared errors. So our variances of yi are going to be compared similarly like the betas were. So our variance of y sub I hat is always going to be less than or equal to our variance of y sub I star hat. This is that the variance of a predicted value from the subset is less than or equal to the variance of the predicted values from the full model. So even though the variables deleted have non-zero coefficients, the coefficients of the retained variables may be estimated with smaller variances. So now section 11.4 is going to discuss some of the main uses of regression equations. So the first is going to talk about description and model building. This is used to describe a process or as a model for a complex interacting system. So the two conflicting requirements here are that we need to account for as much variation as possible. And we also want to try to describe the process in as few variables as possible. In this case, try to choose the smallest number of predictor variables that accounts for the most substantial part of the variation in the response variable. So we always want to try to make sure our models are as simple as possible for us to work with, just so we have like a smaller number of things to keep track of and computations to do. So we want to try to knock down to as few variables as possible, but we want to make sure that we're not leaving out any part of the data or the study. So the second part talks about estimation and prediction. So we can estimate the value of a future observation from a regression equation, or we can estimate the mean response corresponding to an observation from the regression equation. So the third part is control. So this can be used to determine the magnitude by which the value of a predictor variable must be altered to obtain a specific value of the target variable. So standard errors of a regression coefficient must be small in this case. So all these three are very useful, and like we've dealt with these in the past, but regression equations have many uses which are helpful to us in our computations and our studies. So all of these uses usually overlap in studies. So this proves to us that a subset of variables may be a good fit in one situation, but not in a different situation. It is important to keep in mind that there is no best set of variables. So you can be doing the same study as someone else and have a completely different set of variables. It's all up to what you think is going to help improve your study and help efficiently complete your study to the best of the best that you can. And there's also no right way to determine variables. So so the next section is section 11.5, which is going to talk all about criteria for evaluation equations. So the first is the residual mean square. So this is used to measure the adequacy of a fitted equation. And this is going to be represented by RMS for residual mean square, and then a subscript of P. And we're going to find this by finding our SSE value of P, and we're going to divide that by our N minus P value. And our SSE sub P is going to be the residual sum of squares for a P-term equation. The smaller the RMS is preferred in this case. So our R squared value in this case for a P term is going to be computed by our R squared sub p, that's how it's going to be denoted, and it's going to be computed by taking 1 minus n minus p times our RMS sub p value that we found earlier, and we're going to divide that all by our SST. And then we, like we've seen in the past, we can also have an r squared adjusted, which is going to be denoted by r squared sub AP. And we're going to find that by doing 1 minus n minus 1 times our RMS sub p value from before, and we're going to divide that by our SST value. So our r squared adjusted is more appropriate when comparing models with different numbers of predictors. The next equation or statistic that we found here is going to talk about our Mallow's C sub p. So the standardized total mean squared error of prediction is measured by, which is going to be denoted by J sub p, and we're going to find that by 1 over sigma squared times the summation of I equals 1 to n of our MSE value of our y sub I hats. So our MSE of y sub I hat is the mean squared error of I, and our predicted value from a p-term equation. Yeah, so the mean squared error, the MSE of y sub I hat is our mean squared value of the ith predicted value from a p-term equation. So that's how we're going to find our J sub p value. And our sigma squared is going to be the variance of our random errors. So to estimate J sub p, we can use the Mallow statistic. So the Mallow statistic is going to be denoted by C sub p, and we're going to find that by our SSE sub p value, and then we're going to divide that all by sigma squared hat plus 2p, 2 times p minus our n value. And the Mallow statistic is going to measure the performance of the variables in terms of the standardized total mean square error for the observed data points. So this takes into account both the variance and the bias. So you need to transform this measure to a graph of C sub p against p to find which subsets are indeed good subsets. We also want to make sure to include the line C sub p equals p in our graph, so we can see which points are close to that line, and whichever points are close to that line are our desirable subsets of variables. Our next criteria is our information criteria. So our AIC for a p-term, and our AIC is our ACACI, I don't know how to pronounce that, sorry, information criteria, which is going to be represented by AIC sub p. And we're going to find that by taking our n value, times that by ln of SSC sub p divided by n, and we're going to add 2p to that. So we're looking for smaller values in this case. The smaller, the better. This is mostly used to rank models on the basis of criteria of fit, as well as simplicity. So the advantage here is that it allows us to compare non-nested models. So we need complete data in this case, so which means no missing variables. And a popular variation to our AIC is a BIC, which is the Bayes information criteria. So our Bayes information criteria is denoted by BIC sub p, which is equal to n times our ln value of SSC sub p divided by n plus our p sub times ln. So pretty similar to the AIC, only really difference is instead of adding by 2p at the end, we're going to add by p times ln of n. So this tends to control for the overfitting tendency in the AIC model. This is another variation to So another variation in this case to avoid overfitting is the controlled model of AIC. So the AIC tends to include a lot of overfitting in it. So the two ways we can avoid that is by using BIC or by the controlled AIC. So the controlled AIC is denoted by AIC sub P with a C up top for controlled. And then we're going to find this by AIC sub P, which we found earlier. And we're going to add to that with the numerator of 2 times P plus 2 times P plus 3 up top. And then we're going to divide that by N minus P minus 3. All right, so I think that's going to end our video for today. So just to go over quickly this video, we went over variable selection, consequences of deleting a variable, the different uses for regression equations, and the criteria for evaluating different equations. So thank you guys again for watching. Any questions, like always, just let me know, and I'll see you next week. Have a good one.